So first of all, as Connor mentioned, happy Pride, everyone. And I'd like to thank the organizers for giving me an opportunity to speak. And yeah, so something that I want to say from the beginning is that we're already short on time, but uh, so initially it took me a while to actually realize that it's supposed to be a 30 minute talk. So I have prepared slides thinking that it's a 1 hour talk, so I might have to speed run through a few things. And also because of the fact that I'm not usually, I don't have a lot of experience talking to a general category theory audience. I'm more of a stable homotopy theorist myself. But yeah, here goes nothing. So, right, so here's an outline of the talk. So basically, yeah, because we have a very general audience. I'll try to go in as much details as possible, but we'll see how it goes. So here's the outline. Right. So Jacob Lurie in high algebra gave us Starship level understanding of associativity in the formulas of Infinity-Operads. So basically, we have Starship's associahedra that all of us know about. So Lurie basically that he constructed a so we have a converging filtration that looks like the following. And here this A infinity NU is the non-unital associative Infinity-Operad. And this ANUK, this parameterizes multiplications that are associative up to K inputs. So there's a sense in which we can think of this ANUK as the K arity restriction of A infinity. So here's how that makes sense. So this map that we have, so this induces an I don't know if you guys can see my cursor, but so this induces an equivalence on n array morphism spaces for n less than equal to k. And the n array morphism space for n greater than k is generated by less than equal to k morphisms in a suitable sense that we'll see later. So this motivates the natural notion of a k-restricted Infinity-Operad, where we only consider n-array morphism spaces for n less than equal to k. So thus k-restricted Infinity-Operads, you can think of them as k arity skeletons of Infinity-Operads. So Hertz constructed this category that op nu less than equal to k, so this is basically the infinity category of non-unital k-restricted Infinity-Operads. So if I'm not wrong, so this was in Hertz's thesis in an appendix. And so he basically proved that the natural restriction functor that you have from this category of non-unital, infinity category of non-unital Infinity-Operads to this k-restricted category. So this basically has fully faithful left and right adjoints. So we are basically interested in the unital versions of these k-restricted Infinity-Operads. Why unital, you might ask? So I'll probably, okay, towards the end of the slide, I'll say a few things about that. So yeah, so we'll just take a peek. So because of the time constraints that we have, I'm pretty sure won't be able to see more details. So this is the main theorem. It should make sense towards the end of the talk. So this functor, so this functor that you have, so this admits left and right adjoints, which we call LK and RK, which are given by left and right Kohn extensions along this. So I hope that this will make sense towards the end of this talk. So yeah, given the fact that I have 30 minutes, so the most important, the goal that I have is to explain to you guys what a unital k-restricted Infinity-Operad is mostly, and then talk about the right and left adjoints if time permits, which I don't think will be the case. So let's recall. So let's just go through the definitions real quick. So a finite rooted tree. So here's it. So I'll kind of speed run through these sections given the limited amount of time that I have. So here I basically define what I mean by a finite rooted tree. So a dendroidal tree basically, so it's like a pair of a tree and a set of maximal elements. We'll just denote that by the tree, right? So this omega is the category of dendroidal trees. So we define this omega, the category of dendroidal trees, with the objects being trees and morphisms defined as follows, right? So, and then a tree is said to be closed if the set of leaves L that we had is empty. So we denote by omega C, superscript C. So that is the full subcategory of omega, considering consisting of closed. So yeah, so it's an easy thing to notice. I mean, you can figure this out probably that so you can explicitly. So okay, it's not even an exercise. I mean, it's pretty easy to see. So this omega C is so it's like a category with objects being finite rooted trees and morphisms being order preserving maps that preserve independence. So now here's a proposition that we'll use later. So this omega C, it's basically the category of mu local objects. And okay, so I'll define what this mu is, hopefully. And for any closed tree T, the unit map from T to TC is a localization relative to mu. So here, okay, yeah, here this mu denotes the unique map from eta to C naught, where eta is basically the dendroidal tree with one edge. So now the key idea is to think about factorization systems on this omega C. So we'll see how that comes into play. So here are the morphisms of interest that we care about. So first we take a morphism F, it is said to be rooted if it takes a root to another root. And similarly, we define subtree inclusions and max surjective inclusions. So we'll see these are really important. So, and we'll call these rooted max surjective maps active and subtree inclusions inert. So the classes, this class is consisting of max surjective maps, rooted subtree inclusion. These morphisms, these form a factorization system on omega C. So I mean, I'll not go through the proof sketch. I mean, the uniqueness part is pretty straightforward. So if you take a map from T to T double dash, and you suppose T dash is a rooted subtree of T double dash that consists of all these edges, such that there exists another edge E, as you can see here, since the FE is greater than or equal to E dash. Right. So therefore you'll get a factorization through this T dash, and then by construction you'll get that this map from T to T dash is max surjective. Right. So similarly, we'll also see that the classes of morphisms of rooted max surjective maps and subtree inclusions, these form a factorization system on omega C. So you basically have a factorization like this. So if you take a morphism in omega C, you can factor it by rooted max surjective maps, max surjective subtree inclusions, and rooted subtree inclusions. So you have such a unique factorization. Right. Now getting to dendroidal trees. So a tree is called dendroidal if every edge is said to be k-dendroidal if every edge has valence less than or equal to k. So this is our full subcategory of omega and respectively of omega C, which consists of closed dendroidal k-dendroidal trees. So an important corollary of this of the last proposition. Let's go to the proposition real quick. So when I say last proposition, I mean the proposition. Yeah, this proposition. So the fact that it is the category of mu local objects. Right? So from that, basically, it follows that. Okay. Yeah, from that, basically, it follows that the localization functor that you have from omega to omega C that restricts to a localization functor, the k restricted sense. So we'll also see that these k-dendroidal trees satisfy very important closure properties with respect to these max surjective maps and subtree inclusions. So you take a map in omega, and if F is a subtree inclusion and K is a k-dendroidal tree, then this K is also a k-dendroidal tree. Okay, I believe there's a typo here. Never mind. So, and then if F is a max surjective map and K is a k-dendroidal tree, then K is also a k-dendroidal tree. So now we have the k-dendroidal analog of the last two propositions, which is basically that the classes max surjective maps and rooted subtree inclusions, and the rooted max surjective maps and subtree inclusions respectively. These form factorization systems. So, okay, so now, right, so I think I'm on time, so right, good. So, right, so in this section, we'll basically try to define what a unital k-restricted infinity-operads is. So the model that we are using is basically as complete Segal presheaves. So this basically builds on work by Clark Bauwek and a work by Shu, Hoxhang, and Hertz. So right, so here basically I define what, yeah, right. So this is a subcategory that I'm defining. So this basically consists of all these morphisms from X to T, such that X is either the edge mu or the corolla M, and F is a subtree inclusion. Furthermore, if X is an N corolla with root Z, then F of Z also has valence Z. So we now see, yeah, we now see the Chu Hoxing's definition of Segal presheaves. Just to recall, so if F is a presheaf of omega, then it's a Segal presheaf for all trees, this map that we have here. So this is an equivalence. So now the point is that we generalize this to Segal presheafs over this category, omega C less than equal to K. Right. So right. So first we take first we fix a K, and then we take a presheaf on omega C less than equal to K. Then it is said to be a Segal presheaf if for every K tetroidal tree, this map that you have. So as you can see, this is, so you're just taking X of C. So this is an equivalence. So this is just the analog. So now we'll basically define this category, subcategory of which is basically a full subcategory of Segal presheaves by this CSEG, C of C. So a quick remark. So if we have a map of Segal presheaves on this category omega CK, so I'll call this omega CK from now on forward. So it follows that it follows from the Segal condition that F is an equivalence if and only if this map that you have is an equivalence for all these i's between 0 and k. Right. So our next goal is to relate Segal presheaves on omega and omega c. So this spellback functor that you have, so this is my presheaf category, this P. So this preserves Segal presheaves. Then the induced functor between the Segal categories is fully faithful. And the image of this functor, this consists of Segal presheaves F on omega such that this map is an equivalence. So sorry, yeah, so we'll see an useful criteria which we in fact use in our preprint for the Segal condition. So I believe I have 17 more minutes left. Is that right? Just checking with you guys. Okay, thanks. So, right.
If you want to take questions, you might want to cut it off at 12 minutes, but 17 minutes for the rest of the talk, yes.
Thanks. Thanks a lot. So, right. So now we define what an upper subtree is. So an upper subtree of T with root E. And similarly, we have the notion of a lower subtree of E with leaf E. And we call this the subset of minimal elements of this T greater than equal to E by V of E. So this comes in handy. So now we start with a presheaf on omega, then the following are equivalent. It is a Segal presheaf. And then for every tree T and an inner edge E, this map that we have, this product. So it's an equivalence. And the other statement is for every tree T and a non-maximal edge E naught of T, this map right here is an equivalence. And there's a fourth statement that is for every tree T, this map right here, this is an equivalence. Right. So now we basically move to the k-dendroidal setting. So all this is pretty standard stuff, which is why I've been kind of skimming through a lot of it and not spending a lot of time. So, right. Right. So we start with the presheaf on omega ck. So then the following equivalent. this presheaf F satisfies the Segal condition, and then for every K restricted closed dendroidal tree T and inner edge E in T map. So as you can see, this is analogous to the previous proposition that we saw. So this map is an equivalence basically. And then similar to the last proposition, so again, if we start with a K-restricted closed dendroidal tree T and a non-maximal edge E naught of T, this map that we have here, this map is an equivalence. And similarly, so we also have another equivalence statement as we had in the previous case. So now, right. So this is the whole point. We'll define complete Segal presheaves in the closed k-dendroidal setting. So again, we fix this k and j, and so C is something like it can be omega c, omega c, k. So a Segal presheaf on C is said to be complete if the Segal space is a complete Segal space in sense of rest, right? So R is basically the inclusion that you have from delta to omega. So we are basically abusing this to denote, right, the composite, so this composite, as well as its factorization through this omega ck. So now, so this is our notation for the full subcategory of complete Segal presheaves. So now, following Joyal and Tierney, so this is equivalent to category of infinity categories, cat infinity. So now, so here's a remark. So these functors that we have, so these preserve and detect complete objects. And yeah, so we'll denote these functors, like for brevity, we'll denote these functors and complete Segal presheaves by the same symbols. So again, now this is the central theorem. I say it's the central theorem because this is like, this is most of the foundation. So this is like the whole thing that we are working with. So we have an equivalence. So this is based on work by Clark Barwick and Shu Hoxang Hoyts, that we have an equivalence of infinity categories between the category of Infinity-Operads and this complete Segal presheaves. So under this equivalence, the edge eta, this corresponds to the Infinity-Operad triv, and then Cn corresponds to Freer. Right. So now recall what unitality means. So in Infinity-Operads is unital for every color X. This small also, okay. So this is my notation. So this is contractible. And so the full subcategory of unital Infinity-Operads are just denoted by op-un. And so basically, the idea is that the equivalence of the last theorem just restricts to the unital cases. So following the last corollary, we have the following definition for k-restricted unital Infinity-Operads. So this is basically, this is a complete complete Segal presheaf on omega ck. All right. So okay. So this will be our category of k-restricted unital Infinity-Operads, and so these two are the same. And this is our functor. So this is basically the this is basically the functor where you are taking the complete Segal presheaves from omega c less than equal to j to complete Segal presheaves from omega c less. So we have fixed j and k, remember. So now, so suppose f is a unit. So now that we have the notion of unital k-restricted Infinity-Operads, so let's let f be our k-restricted Infinity-Operads, and so this is the space of colors. Additionally, if we have colors from x1 to xn and y in f, so this is basically the fiber product. So this is our notation, and so now, right. So here's a remark. So suppose we have a map between unital k-restricted Infinity-Operads, and the following are equivalent. So f is an equivalence, and then for any k, this map is an equivalence. Similarly, the induced map on colors from f1 C0 to f2 C0. So this is an equivalence. Furthermore, we have so this induced map that we have. This is an equivalence, right? So we're almost running out of time. So Right. I also want to talk about left and right adjoints. So that's spirit. Let's move on. So now pulling back complete Segal presheaves along R. So this basically gives us a functor between complete Segal presheaves. That is characteristic to Unital-Operads to the category of to complete Segal presheaves on delta. That is basically cat infinity. So this functor, so this basically takes sorry, this basically takes unital k restricted Infinity-Operads to the underlying infinity category. So yeah, so I'll not get into the technical details given the fact that I have like few more minutes. So I'll just state the theorems and maybe talk a bit about how we prove it, which is a bit technical. So anyone interested can catch me or my co-author Leon later for more details. We'll be more than happy to chat. So this LK is a left adjoint, so we have an adjunction. Furthermore, the left adjoint LK is fully faithful. There seems to be something wrong, but okay. So we thus have a colimit description of the multi-array spaces of F. Uh, okay, I see. Okay, there seems to be an issue for which I'd like to apologize for this. So there seems to be a slide missing from my slides, but okay, we'll see if we have it in a different place or something else. But okay, for the spirit of the seminar, let's move on. So yeah, so if we write the so if we just write this co-localization functor simply by that is basically LK composed by this as just LK, and if O is a unital Infinity-Operad, then we get a filtration. And the kth stage is the kth arity approximation as they agree on less than equal to k morphisms. So this basically implies that if you take in unital Infinity-Operad, this canonical map is an equivalence. Right. So now moving on to the right adjoint. So yeah, similar to the left adjoint case. So there's, as I said, there's a lot of technical details, especially in the case of the right adjoint happening, which I don't get to talk about now, but can talk about it later if anyone's interested. So yeah, right. So we have an explicit description of the multi-area morphism spaces of F, and voila. Okay, I have. Yeah, okay, there seems to be a problem in the left adjoint case where there seems to be a slide missing, but good for me that okay, I have this slide for the right adjoint in order. So here's the description. So so F is a unital k restricted Infinity-Operad for n greater than equal to k. So this, so this seems to be really technical, but I mean, at the end of the day, the thing is that these n-array morphisms of RKF, so this is the space of collections of less than equal to k array morphisms that are compatible under taking units. So quote unquote taking units. So at some point in the talk in the beginning, I said that we can possibly generalize to this to k restricted Infinity-Operads, but the problem comes when it comes to the right adjoint. So the thing is that so for the right adjoint, there's a problem as in how do I put it? So okay, okay, I'll say more about it after we go through this section. So right, right. So okay, so we can detect a unital k restricted Infinity-Operad in the image of RK. So right, here's another corollary. So if you take in a unital J-restricted Infinity-Operads, so it is the following are equivalent. So F is in the image of RK and this. And then so this map is in equivalence. Furthermore, if you take scholars from X1 to Xn and Y, so then this map is in equivalence. So right, so similar, so this would be my last slide, I believe. So the map, right, so this is an equivalence on less than equal to carrier morphism. So this implies following. So this we get this equivalence. So yeah, that's the end of my slides. Thank you everyone for listening, and apologies for the timing and everything. Thanks.
So am I right in thinking that Infinity-Operads are like monoidal infinity categories, but sort of like a different representable version of that? Um, but I didn't see anything about monoidal infinity categories, so I'm curious if there's a connection there. Not that I know exactly what that is either.
Right, right. No, I mean, so I've given this a thought, but not actually thought about it too much. I mean, the thing is that this was basically so this was part of a project, and the goal was to actually prove a generalized Blacker's Massey theorem. So there was another preprint that my co-author had. So there is En algebras in M categories. That is basically a generalization of the Ekman-Hilton argument. So yeah, I'm not exactly. I'm probably not the right person to answer this question, but thanks for the question. I guess not thought about it.
Yeah, I'm just thinking because, right, operads are representable monoidal categories. So I'm hoping it's true in the infinity world as well, but I'm not sure.
Right, right. Yeah, yeah, that makes sense. But yeah, I'll probably have to think about it. Give this a thought before answering that.
Fair enough. Thanks.
But yeah, thanks for the question.